This is the first of two lectures covering various techniques in calculating electric potential due to various types of charge distributions. For example, if the charge distribution is symmetrical such that Gauss's law can be used to calculate the electric field, then calculating the potential difference between any 2 points in space follows a specific procedure. In the second video, in a little while, we'll see what happens if you have asymmetric charge distributions such that Gauss's law cannot be used to calculate the electric field. We'll go through that process in the next video. Let's go ahead, however, and take a look at the following problem to illustrate what happens when you can use Gauss's law to calculate the electric field. So please write down the following problem, copy it into your notes. Okay, so techniques to find electric potential. Gauss's law can be used. So we have a conducting sphere. It has a charge of capital Q and a radius of capital R. A nice example to place this into context would be the spherical conductor associated with a Van de Graaff generator. Part A, find the electric field everywhere. We'll do a brief Gauss's law calculation to do so. And then B, find the potential everywhere. Okay, so we have here techniques for calculating electric potential. And specifically here for this problem, Gauss's law can be used. Okay, so here is our situation. We've seen this situation before when calculating the electric field. We have here the spherical conductor of radius capital R, and it has a charge Q. So we work from the inside out when doing a Gauss's law calculation. Recall from earlier lectures that once the electrostatic equilibrium situation has been achieved, there is no net electric field inside the conductor. So if we set up a Gaussian surface with a radius here of small r, and once again, of course, that Gaussian surface is a sphere, then for small r less than capital R, the electric field is equal to 0. Okay, but then outside, of course, we just have the electric field due to a point charge. So recall this calculation. Let me go ahead and draw the electric field here. Like so. So here's a few different field lines. Like so. Okay, and then here's our spherical Gaussian surface. Like so. Of radius small r. So now we see what happens when r is greater than capital R. Okay, so just for a little bit of review, we'll set it up from scratch here. So here's Gauss's law. Okay, and then on the left-hand side of the expression, we'll have our electric field E multiplied by the surface area of the Gaussian sphere, or by R squared. This then equals the Q enclosed, which is big Q, and then divided by epsilon naught. Like so, and then here's our electric field as we've seen before. Like so. Okay, now when it comes to part B, this is of course what is new for this problem, finding the electric potential everywhere. What we do is we start at infinity, where the potential is 0, and then work our way inwards towards the sphere. So then therefore we'll start at infinity and end up at a distance small r that is greater than capital R for the first portion of this calculation. So I'm going to refer to this as part B in the problem. So now for part B, as we work through it, we're going to be using this expression here to calculate potential difference. Okay, we can use this expression here because we already know what the electric field E is, for example, from our Gauss's law calculations from earlier. Okay, so now we started infinity. That's going to be point A in the calculation, and then point B in the calculation is going to be a distance r away from the sphere where little r is greater than capital R. So we're specifically working with this portion of the problem, and then we write the following. Potential at position R minus potential at infinity equals then integral from infinity to position R of electric field. And we integrate, of course, in the radial direction. Okay, so the potential at infinity is 0. Okay, and then the integral of negative 1 over r squared dr is positive 1 over r. And we integrate from infinity to r. So plug r into the expression and you basically just get the expression, and then minus with the infinity plugged in, so minus 0. So ultimately then the position, or rather the potential at position R ends up just being the following expression, like it is, for example, due to a point charge. Okay, now we continue to work our way inwards. So now what we're going to do is we're going to get to the surface of the sphere itself. In order to find the potential at the surface of the sphere, we set in this expression here, small r equal to capital R. So now specifically, we look at the potential rather at the surface of the sphere, and then therefore at the surface of the sphere, we'll write it like this, the potential is then equal to the following expression. Okay, let me do a little bit of erasing here. Once again, this calculation from earlier was for small r bigger than capital R, and now we're at the surface of the sphere. And now we go inside the sphere. So when we go inside the sphere, what happens? Well, keep in mind that because this is a spherical conductor, the net electric field inside is equal to 0. So then therefore you would be tempted to say, okay, well then the potential is equal to 0. No, that's not the case. Because the electric field is equal to 0, and then therefore the electrostatic equilibrium situation has been achieved, this then means that the entire sphere is an equipotential surface. Every point within the volume of the sphere itself, if you will, is like at the same height, if you will, in terms of the topographic map. So this then means that the potential at the surface of the sphere is the same as the potential as anywhere inside the sphere. Once again, the reason for this is because the net electric field is equal to 0. It's as if all the charges that may be there are all at the same height, if you will. The entire surface of the sphere and the volume of its interior is an equipotential surface. So for small r less than capital R, this then means that the potential is once again this value, the potential at the surface of the sphere. Sometimes you'll be asked to graph out this problem in part B, graphing out the potential as a function of small r. You'll typically see this, for example, as a multiple choice question on the AP Physics C exam. So then therefore, if we're graphing out here the potential as a function of small r, let's say it right here is capital R. As we go from r is equal to 0 to capital R, the potential is this constant value. So then therefore we have a horizontal line at that value like so. So right over here is the potential at that value. And then as we go outside of the sphere, then the potential drops off as a 1 over r relationship, essentially looking something like this. And then the potential at infinity, once again, is equal to 0. So this problem here covers the basic techniques that we use to calculate potential difference if, yes, we can use Gauss's law to calculate electric fields. It's basically a two-step process. The first part of the process is part A. You work from the inside out using Gauss's law to calculate the electric field. And then you work from the outside in part B of the problem, coming in from infinity, as we've done here, to calculate the potential at various locations in the problem.